Okay, so last section for this week is 5.4. And we're going to do part 1 of it today, and as I said, part 2 after we come back from Thanksgiving. So we study exponentials. Okay, exponential functions are functions that have a number in the base that's positive, except what number is it not allowed to be?
0.
Well, 0, by saying it has to be positive, that covers that part of it. But there's a positive number that it can't be. It can't be 1. So it's any number in the base except 1, a positive number except 1. And the variable is in the exponent. And that causes the graph to curve up very quickly. Well, logarithms are the inverse of that. Okay? They curve up extremely slowly. Okay, so we'll look at some pictures. So a logarithmic function is the inverse of an exponential. What does that mean? It has the same relationship that squaring a number and square rooting a number do. One undoes the other. Adding to a number, subtracting from a number. They cancel each other out. Exponential, log, they cancel each other out. Okay, they're inverses. And I have a picture I'll show you in a second, but what an inverse is it's a mirror image. Okay, visually, if you want to know, well, I have a function, what would the inverse look like? It's a mirror image of it. But it's not a mirror image over the x or the y-axis. It's a mirror image over a diagonal line, y equals x. Alright, so let me fix that because the calculator can't really draw it properly. So what you're looking at in blue is an exponential. What you're looking at in red is a log. That black line is the line y equals x. It has a slope of 1. It goes right through the origin. It cuts the first and the third quadrant on a 45-degree angle. If this was a piece of paper, if you were to fold it right on that black line, the blue graph would land on top of the red graph. Does that make sense? That means they are inverses of each other. They are mirror images over the line y equals x.
So those share, I don't know if it's like the same, but would those share an asymptote? Or like, were they like, because like I know one of the ones we were doing earlier, like they wouldn't get to that same center point on this one, so like cross that center point?
There is an asymptote. So in the blue graph, you have a horizontal asymptote at y equals 0. Right? Because the blue graph gets closer and closer and closer and closer, but it never actually touches the x-axis, even though it looks like it does. In the red graph, because it's a mirror image, all of a sudden you go from having a horizontal to a vertical. So in this case, there's a vertical asymptote at x equals 0. It's switched. So yes, they both have asymptotes, but they are different. Yep. And again, the way I drew it in red, it does look like it touches the y-axis, but it doesn't. It's just because my pen has thickness and I can only draw it so accurately. Alright, so next thing is, when you have something with the word log, how do you read it? Okay, how do you pronounce that? And the way you pronounce it is y equals log base a of x. That's how you say it. And if you were writing it like actually on lined paper, just to show you the placement of how the letters would look, okay, y equals, and I'll just make up some numbers, log base 3 of 2. It's not that the 2 is an exponent. The 2 is right on the line with everything else. That would be an exponent, 2 to the 8th. So the 3 is actually a subscript. It's below the line. The 2 is right on the line. Okay, the 2 is not an exponent. Okay, so that's y equals log base 3 of 2. in this problem, the 2, or in the original problem, the x, that's called your argument. All that means is it's the thing that you're plugging into the log. It's what are you taking the log of? In the problem on the left, you're taking the log of x. In the problem on the right, you're taking the log of 2. Okay, all functions have arguments, like this. Normally we call that the radicand, but technically you could call 37 the argument. It's the thing you're taking the square root of. Okay? That's the thing I'm taking the log of, with a certain base. And we'll learn how to calculate that in a little bit. Okay, so x is the argument.
How would you plug that in on a calculator?
There's no way to directly plug that in. We have to use a special formula, which I'm not going to show you until next time.
Okay.
So if you have a calculator like this, just a regular scientific one, there is a way to do it. But for now, I'm only going to show you how to type in 2 of them. Okay? And I'm not going to show you the case where the base is a 3. Okay? I'm going to show you where it's a 10 and where it's an e. And the reason I'm going to show you those 2 is because they are built into the calculator. You have a button for base 10 and you have a button for base e. Any other base, you need to know something else. I'll teach you next time. So if the base is a 10, okay, so the problem I made up, I had a base 3, that's different. But if the base is a 10, that's called a common log. Base 10 is one of the 2 bases the calculator can do for you by pressing one button. Okay, so base 10 is called the common log. So this is an example of a common log. I want you to find the log base 10 of 8. Or I could also say, I want you to find the common log of 8. Same thing. Now, another way you can write that is you can just leave the base off. This is the only type of log you can leave the base off, the common log. If you write the word log and you don't put a base, it's always assumed you're doing it with a base of 10. So if you write log, you don't put the base, it's assumed you're doing base 10, or common log. Right, so try to remember that. Okay, log by itself, it's kind of hiding what the base should be, but you have to remember it's a 10. Because we're going to do something that requires you to remember that. Question?
No, it's
no. Now the other special log has a base of e. That was that number I showed you yesterday, 2.718. And we did it in a couple homework problems. Does anybody remember what that log was called? Began with an N? Yeah? The natural log. So the only other log that has a special name is if the base is an e. And that's called the natural log. Natural log is the other logarithm that your calculator can do for you automatically by pressing one button. Okay, so when they make the calculator, they have to pick how many buttons do you want on it for log. Because the base can be anything. 2, 3, 4, 6, 12.5. But you can't put a button on the calculator for every single possible base. So the 2 they choose are common log, they give you a button, and natural log. Now, if you look at that black rectangle, if you look at the calculator, or look at yours, you're not going to see this written on it. This log base e of x. There's a button on there that does that, but it's not written that way. Does anybody know how the button that does that is written on the calculator? Yeah?
Would you press second and then press the LN button?
You don't have to press second, just LN button. Okay. This button that says LN represents what I just wrote right there. Okay, so LN is a shorter way of writing log base e. Where does LN come from? Natural logarithm. So why isn't it NL? I don't know. It's LN. So anywhere that you have a log base e, you're going to see it written this way. Lowercase l, lowercase m. LM. Okay, so if somebody asked you to say find log base e of 5, or they said find the ln of 5, it's the same question. Log base e is the ln. The only disadvantage with writing it as ln is the base is hidden. You have to remember, when you write it that way, it's hiding a base of e. So any questions on the two special logs? Common log, natural log. Okay, how do you type it in? Like, let's say you wanted to find the common log of 8. So it's very simple. You just type in log 8. That's it. It's the log of 8. And the calculator is assuming what base there?
10.
10. If I wanted the natural log of 8, type that in. And what base did the calculator assume there? 8. Yep. Those are the only two the calculator can do by pressing a single button and then hitting enter. As far as other bases, you won't have to worry about typing those in on the calculator for this test. Alright, so I'm going to go back for a second and just look at the graph that we had for logs. Actually, you know what? Let me make a copy of it and just move it to that page. Alright, so for this, just focus on the graph in red. So if you look at the graph in red, it's going to go to the right forever. Okay, I chopped it off on the screen because I can't show it forever. But it does keep going. So the domain goes to infinity. But it doesn't go past 0. Okay, follow it to the left. It's like it hits a wall at the y-axis, and it just goes down. And that's because you cannot take the log of a negative number. Okay, if you try, this is what happens. It says it's a non-real answer. So if it's not real, what kind of answer would it be? It would be imaginary. Okay, so we're not dealing with imaginaries. So anytime you take the log of anything, doesn't matter what the base is, it has to be a number bigger than 0. Okay, you can't even do 0. If you try log of 0, you get an error for that too. The range. It goes down forever, and it's going to go up forever. Okay, it's extremely slow. It's kind of like that, but it's still going to just keep going up. Very, very slowly. In fact, if you put in, just put in log of x and look at your table. If you go up to 10, which would be the edge of the normal window, your y value is at 1. Let's say you go all the way out to 500. So you go a lot further to the right. Your y value only goes up to 2.7. Okay, so you went 490 units to the right, and your y value only went up a little bit. If you go to like 10,000, the y value is only at 4. So yes, it does keep going up, but it goes up extremely slow. That's why it's the inverse of an exponential. It goes up very, very slow. Any question on the domain and range of logs? I didn't show it going down forever, but if you tried like the log of 0.00000001, you'll get a negative number. Okay, further and further down, the closer and closer you get to 0. All right, so when you're solving an equation with a log in it, or if you're trying to solve an equation that looks like this, you're going to convert it between one form or the other. What I read here, that's exponential form, because it has an exponent, it's a variable. To solve this kind of problem, you would have to convert it to log form. So in the formula I'm about to show you, I'm assuming that a is a number greater than 0 and not equal to 1. It's kind of the same condition we had yesterday with exponentials. Yep.
How would you write like exponential form using only variables, like as a base to go off of?
Yeah, I'm going to show you right now. So if you used all variables,
Okay.
it would look like that. Instead of a 2 and a 5, you just have like an x, an a, and a y. Okay, so this is more of it's a pattern. You just have to look at what goes where when you rewrite it. The box in blue, that's your base. When you pronounce it, log base A. When you rewrite it as an exponential, the thing that's below the exponent is called the base. So the base on your log becomes the base on your exponential. So the base stays as the base. The next thing I'm going to look at is the y. And if you remember the following sentence, you'll always remember what y is. Logarithms equal exponents. Anytime you do log of anything, like let's say I type in log of 8. Okay, I just did that. 0.903. That number is an exponent. What's it an exponent to? Well, whatever the problem was that caused me to type that in. Log of 76. 1.88. 1.88 is an exponent on something, whatever the problem was. Right? So when you do a log, it always equals an exponent. The answer is an exponent. That's why the y goes as an exponent. And then if you know where the a goes, you've got that, and you know where the y goes, well, if you're going to make an equation out of it, you've got to put something on the other side, so the only spot left is to put it on the left. Okay, we'll practice a few problems where we change log to exponential and then the other way around. Okay, does everybody have the formula? Okay. So, let's change that to exponential form. All right, so first thing I'm going to look at is my base. Curtis, what's my base here? My base is 3. So when I rewrite this, that's going to be the base, and I'm going to have some exponent right there. So the base stays as the base. Now I need to figure out what the exponent is going to be. What did I just say? Logarithms always equal what? Logarithms always equal exponents. So y is my exponent. Okay, I've used the 3. I used the y. What's the only thing that's left? X, and what is that thing called again? It's the thing you're taking the log of. Colleen? It's the argument. So the argument goes on that side.
It's the what?
The argument. And that's it. There's nothing you can do further with that. Let's say you knew y was 2. Well, then you could solve it. 3 to the second power, and x would be 9. But to get a numerical answer, you'd have to know more information. Any question on how we change that to exponential? All right, let's try this one. Y equals log base 5 of x. Okay, so the first thing to notice when you rewrite it in exponential, the word log is gone. That's the point. You're getting rid of the word log. Okay, so Mylery, what's my base here? Yep. The base is 5. Logarithm always equals the exponent. So Casey, what's my exponent here? Y. And I've got to put something on the other side. I only have one thing left to use. So Caitlin, what do I have left? X. And without knowing more information, that's all you can do. Okay, questions on that? All right, so that's changing to exponential. Let's try the other way. Let's try changing to log. Well, if I'm going to write it in log form, the first thing I need is the word log. Okay, so write that down first. Hannah, what's my base?
1.2.
Right. The base is what's lower than the exponent. Okay, the base is 1.2. That's also going to be the base on my log. Okay, Colin, what did we say? Logarithms always equal what kind of number?
Exponent.
Always equals the exponent. What was the exponent here? 3. So the logarithm is going to equal what the exponent was. And the only thing I have left is the m. And Ian, what is the m going to be when I put it down here?
The argument.
It's going to be the argument. Yep.
So for the m, does it have to be the variable that they used, or can we do x?
Yeah, you want to use what they use.
Okay.
Yep. Any other questions on that? All right, let's try this one. E to the b equals 9. First thing is, how many variables are in that equation?
Oh,
1. How many letters? There are 2 letters, yes. But there's only one variable. E is really the number 2.718. And it goes on, but... Right, so let's rewrite that. Well, Colleen, what's my base here?
E.
Yep. The base is whatever's lower than the exponent. Log base E. Logarithm always equals the exponent. So on that side, I'm going to put B. And the only thing left is the 9. And that's my argument. Now, there's a different way you can write that. Can anyone give me a shorter way to write log base E of 9? And this is probably what I would expect on the test.
ln 9.
ln 9. Now, if you wanted to know what that is, you could just go on your calculator, press the ln button, press 9, and hit enter. Yeah, I don't care what the decimal is. So. Any question on that one? Okay. All right. So this one, it's kind of like a proof. Okay? It says show that what's on the left is the same as what's on the right. Well, what's the only thing that I've shown you how to do right now with an equation that's written in log form? There's only one thing I've shown you so far. Yep. Have a guess? What's the one thing we've been doing so far with log equations? Yeah.
Try to change it to exponential.
Let's change it to exponential. So hopefully by doing that, we get something that answers this question. Josie, what's my base here?
2.
Yep. Base is 2. Braden, what about my exponent?
3.
Right, logarithm always equals the exponent. And Brandon, what's the only thing I have left that I haven't used?
8.
Yeah, sorry.
Oh,
And then
that's
Brandon, yeah.
8.
Is the 8, is 2 to the third power 8?
Oh, wait.
2 times 2
Yeah,
times
it
2?
is.
Yeah. That's true. So if that's true, then that means the original is true. By rewriting it in exponential form, we've shown that it's true. That's all you'd have to do. All right, so this one's similar to the last one, but this time it doesn't say show something is true. They want you to figure out what would be on the other side. Okay, so we've got an equation in log form. We're going to rewrite it in exponential form. If that doesn't work, we don't know what else to try right now. Okay, so Julia, what's my base?
5.
5? What about my exponent? Not the 1 over 25. X, right? Logarithm always equals the exponent. The 1/25th, that's going to go on the other side by itself. Now we have to figure out 5 to what power is 1 over 25. If you're a little confused because it's a fraction, think of this problem, which doesn't have the same answer, but it's similar. Think of 5 to what power is 25, and then think of what kind of number you have to cause it to flip. Yep.
-2.
Negatives, right. If you have negative exponents, that causes your fraction to flip. So the answer to the problem on the right is 5 to the second power is 25. You want to get 1 over 25? Make it 5 to the negative second. -2. Okay, so for now, the number that I give you here is always going to be a power of that number. It has to be. If I gave you one that wasn't, you don't know how to solve it yet. That would be like me giving you this. 2 to what power is 5? Well, 2 to the second power is 4. 2 to the third power is 8. So it's somewhere between the second and third power, but what is it exactly? We don't know how to solve that yet. Or maybe you would on the graphing calculator. To use an idea we've done before. You could probably figure it out. Okay, but we definitely don't know how to do it without a graphing calculator. All right, so the last problem we solved, the variable was on the right by itself. Let's try putting the variable in a different spot. Okay, now the variable is the argument. Anyone think they could tell me how to rewrite that whole thing? Call?
It'd be 5 to the 1.5 power equals x.
Yeah, that's it. 5 to the 1.5 equals x. So now this one, you just type it in. 5 to the 1.5. If you put the 0.5, that works a lot better. So it's about 11.18 if they wanted a decimal. So that's the kind of thing that's going to happen if you put the variable as the argument. So we looked at the variable by itself on the right. We looked at it as the argument. Now we're going to look at it in the base. Can someone different tell me how you would rewrite that one? What did you do there, Andrew?
X to the second power equals 3.
X to the second power equals 3. Yep, looks good so far. And now what do you do to get x by itself?
Curtis? Square root of 3.
Take the square root of 3. Now, technically there's two answers to the square root of 3, positive and negative. But what did we say about negative numbers? Do we use them with logs? No, if you do, it's going to be imaginary. Okay? So the base can't be a negative, the argument can't be a negative. neither one of those things I just circled can be negative. So just take the positive answer, square root 3. Any questions on that? All right. So the last thing we're going to look at is some special properties of logs. The first group of properties I show you, they're more like patterns. It's like if you see this, you should just know the answer, because it's going to follow a special pattern. There's no real algebra or arithmetic to do with anything I'm about to show you. But in the formulas that I give you, I'm going to use the variable a. I'm assuming a is a positive number, but it's not 1. Okay. So first property says if you have a, and then the next box, that's an exponent, a raised to the power log base a of x. That would just come out to x. So what's happening is it's kind of like this one. This number and this number match. Whenever those two things match, what basically happens is these cancel out. Don't draw lines through it because you need to be able to read your notes. But what happens is those are going to cancel out, and the answer is whatever was sitting right there. So when we do this one, basically those cancel out, and the answer is whatever is left. Okay, so we'll come back to that. Okay, so again, it's not really any arithmetic or anything. It's just a special pattern if those two numbers happen to match. Okay, the second pattern to look for. Kind of a similar idea, except now instead of an exponential equation, which was the first one, you have a log equation. Log base a of a to the x. The key this time is those two things match. Okay, what would that look like in a problem? It would look something like that. Those two things match. If they match, what happens is this cancels out, and the answer is whatever is right there. If they don't match, you can't use that rule. So like if you have log base 3 of 2, well, no, they're not the same. If it's log base 3 of 3, then yes, you could use that rule, and these cancel out. That's the only thing that's left. That's the second pattern. The third pattern says log base a of a equals 1. Right, so something like that, if you had log base 7 of 7, the answer is 1. Log base 12.5 of 12.5, the answer is 1. And really, rule 3 is just rule 2. Because what exponent is on the a right here, even though I didn't write it? Yeah, there's a 1 hidden right there, right? Even though we don't write it. Well, that's exactly what rule 2 is. This stuff cancels out, and the answer is whatever's left right there. So technically, those are really the same rule. And the last special pattern says log base a of 1 equals 0. In other words, if you take the log of 1, it doesn't matter what the base is. The answer is always 0. Okay, so now what I'll do is I'll leave those up. Make it so you can read those again. And what I'm going to do is put some problems on the right, and I want to match them up with the property on the left. Okay, and see if we can simplify. All right, let's start with 6a. Ezekiel, do you see what property 6 6a matches up with? Yep, that's an example of 1 where a is 2 and x, in this case, is pi. So if you apply rule 1 to that problem, what do you get for the answer? Pi. So if you're solving that problem for x, in this case, the answer is 3.14. Let's look at b. Anybody think they know which property that one matches?
Second one.
Yep, it's the second one. So now if we apply the second property to that,
It's -4.
the answer to that would just be -4. Third one is a little trickier. Anybody think they know what property that one is? It is 2. Can anybody rewrite that so it makes it a little more obvious that it's rule 2?
Would just do the same, just make it all except
So yeah, what would you change this to? Log something else.
E.
Log base e. So what I just circled, I just rewrote as log base e. That's the long way to write it. Now copy the rest of the problem. Now it should be clear that it's rule 2 because these match. So what would the answer be? kt, whatever k times t is. I didn't make one up for all the other properties, but I'll make one up for one of the other properties in a second.
Also in a contest, like those would be multiple choice, and you put like there'd just be KT somewhere, and you can circle that, or like KT equals nothing.
If it was a multiple choice, yeah, it could be a short answer just like that too. Yep. How about log base 12 of 1? What would be the answer to that?
0.
0. That's rule 4. Okay. So any question on those properties? So those are properties that you don't really do much work, you just look for a special pattern and then follow the pattern and it tells you what the answer is. Okay, so last group of properties. So these properties are used to think of it as combining like terms. Okay? We can take 2 logarithms and we can combine them together. Or if you want, you can take something that's already combined and you can split it apart. Either way. So the first one is showing you if you have the log of a product. The logarithm of a product is equal to the sum of the logs of the individual factors. That's how you could say that. The log of a product turns into the sum of the logs of each individual factor, m and n. So an example with numbers, right there. Just let m equal 4 and I let n equal 5 and I wrote the same thing. Notice the base always stays the same. Whatever the base was to start with, that's the base you're going to use when you finish. Okay, and you can type that in if you want to. I'll show you one time on the first one. So if I did log of 20, which is 4 times 5, or I did log 4 plus log 5, I get the same thing. What's another way you can multiply 2 numbers to get 20 besides 4 times 5? Yeah, so if you did 10 and 2, that's also going to work exactly the same. Any 2 numbers that multiply to give you 20 would work in this property. Now, I showed you the property and all I did was press the log button. So what base did I use to show you the property?
10.
I used 10. I could do it with any base if I knew how to type it in. But 10 is just the fastest one for me to quickly show you that it works. Alright, so that's the rule when we have a multiplication. What do you think would happen when we have division? How do you think division would split apart? As what? Yeah, it splits as subtraction. You have to subtract it in that order. Log of the top minus log of the bottom. That can't be switched. Because 5 minus 2 is not the same as 2 minus 5. You have to switch the order with subtraction. Ian, did you have a question?
For the top one, can you split 4 into, like, do the property again and split 4 into smaller parts?
Sure, yeah. So you could do the log of 2 times 2 times 5. And you could write that as log 2 plus log 2 plus log 5. Yep, good question. So it doesn't just apply to 2 things, but you could have 3 things, 4 things, as many things as you want. Okay, there's an example again with numbers. I'm not going to type that one in. If you want to check it, you can check it. It works. Okay, so the log of a quotient splits as a difference. And then the last property has to do with having an exponent on your argument. What you're allowed to do with exponents on your arguments is move them in front. There's an example of that property. The reason why you can just put the r in front, it's actually very simple. But I would rather go over a couple problems than explain the reason why right now. Okay, so here's an example. I just put the 5 in front. So when you read directions, if they say something like separate and express powers as factors, what they're saying is do not leave things as exponents. Do not leave powers like this. Put it in front so it's multiplication. And I think when we talked about square roots, we mentioned this. What power is a square root hiding?
1.
Well, 2 is how you would get rid of square root. But what's that the same as? X to the what power? 1/2. That's going to come up in one of our problems. Okay. So if you see anything with a square root, remember that it is hiding an exponent. That's important. Okay. Let's try this one. Separate into multiple logs. If you end up with exponents, move them in front. Put them as factors. All right, so Dave, inside the parentheses there, is that a product or a fraction? It's a product. Does a product split as a sum or difference? Sum. So we're going to have a sum. We're going to have 2 logs because inside the parentheses we have 2 factors. Log. What's going to be the base on each log? It's going to stay exactly the same as the original. What's the argument to my first log? Argument to my second log? X. And that's it. Okay, they get a little harder, but that's the basic idea. That's how we just took a log and we split it into 2. Okay, let's try this one. Log base 2 of 5r cubed. Okay, so inside parentheses, how about Hannah? Do we have a product in there or a quotient? It's a product. It's something times something. Multiplying 2 things together. So a product, how did we say that splits? It's going to split as a sum. We're going to have 2 logs. Each of them is going to have the same base as the base you started with. What's my first argument? 5.
R to the third.
And then my second argument would be r to the third, but what can I do with that? I can move what in front? The 3. The 3 needs to go down in front because it said to do that in the directions. It's a little bit harder, but not that much harder. You just have to move the exponent at the end. Questions on that one? All right, so we tried a couple with products. Let's try a quotient. Log base 9 of x divided by 2. Okay, so AJ, I've got a quotient there, so how is that going to split? Sum or difference? That's a difference. It's a difference of 2 logarithms. Each of them are going to have a base of 9. Julia, what about my argument to the first log? Yeah. Thanks. Getting ahead of myself a little bit. My argument to the first log? Yep, x. And the argument to the second log, I kind of started to tell you, is that. Okay, any questions on that? Okay, let's try this one. So this one is now doing it with log base e. The properties I showed you, they work for any base. Base 9, base 2, base 4, even base e. You don't have to write it as log base e. We're going to stick with the abbreviation ln. But just remember, it's just log base e. Anyone think they could tell me the whole thing of how that would split in one step? If not, you could do it in 2. But yeah. Yeah, Brandon.
Log base e.
And what's the abbreviation for that? We're going to stick with the abbreviation.
I don't know. Log? I am even so confused right now. I really am. But I am. Not even the positive, now I'm confused.
Yeah? Can you just tell me the abbreviation for what you said, and then I'm going to go back?
ln.
ln. So we're going to stick with ln.
Third time.
And what do you think is going to go with that?
That was pretty short. Now it's like, isn't it y to the third or?
Well, you would have y to the third, but then what about the 3? Where does it go?
Okay, I thought I was right. Just call it something else now.
Nina?
Go.
In the front. So it's ln y to the third, but then the 3 goes in front. It's a quotient. So am I going to put a sum or difference? Minus difference? ln 8. Any question on that? All right, I'm going to change the next one. I want to do another product. Yeah.
Can I try to go like the whole thing?
You want, yeah, give me the whole thing? Sure.
ln plus 1/2 ln x.
Perfect. Can you explain why, well, I know why we did the plus because it was a product, but where did that 1/2 come from?
The square root.
Right. Remember that that's really this. So if you write it with the exponent of 1/2, you then have to move it in front. If you write an answer, a final answer with a square root, that's not good. The last one I'll do with you is just recombining it into a single log. So if you can split it apart, combining it is easier because at each step you have less stuff. You're simplifying it rather than complicating it. What would be the first thing you would do here? And we're doing everything in reverse now. So what do you think the first thing you would do here? Yep.
Combine the logs.
So we're going to combine them in a single log, but we have to move something first. What do we have to move? Liam?
The 4 over the exponent.
Yes, put the 4 back as an exponent. That's the last thing you would have done. Now we're reversing. So it's log base A of 7 plus log base A of 3 to the 4th. And in a minute, I'm just going to write what that is. 3 to the 4th is 81. Okay, so in the next step, I'm going to put 81. Now we've got a sum. How would a sum combine? Is that multiplication or division? Multiplication. 7. And that's 3 to the 4th. But remember, I just said 3 to the 4th power is 81. What's the base?
A.
A stays exactly the same. The last thing you'd want to do is 7 times 81. So 7 times 8 is 56. 7 times 1 is 7. 567. So that's how you recombine. Yeah, I just did a little trick in my head. So that's how you recombine. So any questions on that? Okay, so tomorrow, again, that's review day. So we can go over anything from the homework, anything from earlier in the week. We'll have about 40 minutes or so tomorrow. Okay, homework. It's on 292. 1 through 6. 13 to 16. 21 to 23. 25 to 27. And 29 to 32.